And what we want to look at in the first section of Chapter 4 is the development of the new atomic model based on information that was received through new experimentation. So we should be able to explain the mathematical relationship among the speed, wavelength, and frequency of electromagnetic radiation. Discuss the dual wave particle nature of light. Discuss the significance of the photoelectric effect and the line emission spectrum of hydrogen to the development of the atomic model. And finally, describe the Bohr model of the hydrogen atom. In order to get a feel and an understanding for what we're talking about here, we have to start to understand, conceive and work through the concept of light and what light is and the property of lights. So first, light has been in the past described as a wave, and there are wave-like properties of lights. For example, electromagnetic radiation, which is a form of energy that exhibits wave-like behavior as it travels through space. So electromagnetic radiation comes with light, but it has wave-like properties and characteristics. And together, all the forms of electromagnetic radiation form the electromagnetic spectrum. Okay, so this has to do with different wavelengths. Okay, and the different wavelengths of light put whatever you're talking about on different places on the spectrum. So here, again, notice here is the wavelength. This is your electromagnetic spectrum, and you can see where visible light falls. Okay, so obviously it has wave-like properties. If we're able to measure wavelength and then take visible light and put it on the spectrum, you can see where it falls in comparison to the wavelength of gamma rays or X-rays or ultraviolet, or infrared heat waves and microwaves, TV and FM radio waves, AM radio waves. And you can see where everything falls again in terms of their wavelength. Wavelength is lambda. That symbol there is the Greek letter lambda. And wavelength is the distance between corresponding points on adjacent waves. Usually we're going to measure that distance from crest to crest. You could also measure it from trough to trough. It would be the same number. Okay, but it's the distance between corresponding points on adjacent waves. We also, when we talk about the wave properties of light, talk about frequency, which is defined as the number of waves that pass a given point in a specific time, usually 1 second. Usually frequency is going to be measured in 1 second time increments. And we know, as we've done the experimentation and worked some of these things out, that frequency and wavelength are mathematically related to each other. And that is represented in this equation, where c is the speed of light in meters per second, lambda is the wavelength of the electromagnetic wave in meters, and the little v is the frequency of the electromagnetic wave. So this shows us, guys, the mathematical relationship that exists, and we're applying this, of course, to light, the mathematical relationship that exists between frequency and wavelength. This diagram shows, in terms of using the waves of the ocean, how we can measure wavelength. You can see the lambda there from corresponding points of waves. The distance between any two corresponding points on one of these water waves, such as from crest to crest, is the wave's wavelength, which is lambda. And we can measure the wave's frequency by observing how often the water level rises and falls at a given point, such as at the post. this brings us to a discussion of the photoelectric effect, which basically is going to be talking about the emission of electrons from a metal when light shines on the metal. Okay, so understanding this definition, guys, of the photoelectric effect helps you to see how we're going to take this and kind of circle back around and apply this to our understanding of the atom, because this has to do with electrons. Now this brings us to the particle description of light. So what we're saying here, guys, is light ends up being this interesting thing in terms of our understanding of how it works. We can describe light in terms of wave properties, but light is not just a wave. And we can describe light in terms of particle properties, which we're about to do, but it's not just a particle. Okay, so describing light in terms of particle properties brings us to a discussion of quantum. A quantum of energy is the minimum quantity of energy that can be lost or gained by an atom. So this is a pretty specific definition here, guys. A quantum of energy is the minimum quantity of energy that can be lost or gained by an atom. So that's connected to the photoelectric effect. Okay, electromagnetic radiation strikes the surface of the metal, ejecting electrons from the metal and causing an electric current. You can see this here where you have a voltage source, where you have a cathode and an anode, and when that electricity, that energy is hitting that metal source, you get this release of electrons, or this stream of electrons. Continuing with the particle description, this brings us historically to physicist Max Planck, who was German, and what he did, understanding the stuff that we're talking about, proposed that there was a relation between a quantum of energy and the frequency of the radiation. Remember, frequency, you've got to go back to our wave definition and what is frequency. And he says there's a mathematical relationship between a quantum of energy and the frequency of radiation. And that's expressed in this equation, where the capital E is the energy, and this is in joules, of a quantum of radiation. Little v is the frequency, as we've already said, of the radiation emitted, and the little h is the fundamental physical constant, now known as Planck's constant. So here again, guys, we are in another situation where you're looking at a constant number. This is a number that always stays the same. Planck's constant is 6.626 times 10 to the negative 34 joules per second. Going on now with this particle description, we talk about a photon. And a photon is a particle of electromagnetic radiation having zero mass, but it carries a quantum of energy. And the energy of a particular photon depends on the frequency of the radiation. So because of that relationship that Planck figured out, the energy is dependent upon the frequency. And we show that here with this equation. That brings us to the hydrogen atom line emission spectrum. Okay, the lowest energy state of any atom is its ground state. Okay, again, the lowest energy state of any atom is its ground state. So, a state in which an atom has a higher potential energy than it has in its ground state is an excited state. So we can take atoms in their ground state and we can excite them by adding energy to them, and we call that the excited state. When you do that, we end up getting some pretty interesting results. So what are ways that we would increase energy in an atom or put an atom into an excited state? Well, one of the ways is through electric current. Okay, and so when investigators were studying this kind of stuff, they passed electric current through a vacuum tube that had just hydrogen gas at low pressure. They observed the emission of a characteristic pinkish glow. So you have hydrogen, You excite the hydrogen atoms, you put the hydrogen atoms into an excited state using electricity, and all of a sudden you start to see this pinkish glow. When a narrow beam of that emitted light was shined through a prism, it was separated into 4 specific colors of the visible spectrum. So now we take that beam and we split that pinkish glow and we split it up using a prism, and it separates it into its component parts. And the 4 bands of light were part of what is known as hydrogen's line emission spectrum. Now what you're going to see here, guys, is that this line emission spectrum is a property of different elements that can be used to identify the elements in question. Notice here you have this pinkish glow as you excite, right, the hydrogen, and you shine it very narrowly through a prism, and it's broken down into these strips, or these specific visible light waves, and because they are different colors, that means they have different wavelengths, and we can actually measure those wavelengths: 397 nanometers, 410 nanometers, 434 nanometers, 486 nanometers, and then at the far end 656 nanometers. And so what this says, excited hydrogen atoms emit a pinkish glow when the visible portion of the emitted light is passed through a prism. It's separated into specific wavelengths that are part of hydrogen's line emission spectrum. And so Bohr then creates this model of the hydrogen atom. This is Niels Bohr, based on the information that was gathered from that experiment. Proposes a hydrogen atom model that linked the atom's electron to the photon emission. And according to Bohr's model, the electron can circle the nucleus only in allowed paths or orbits. This also becomes known as the orbital model of the atom. The energy of the electron is higher when the electron is in orbits that are successively farther from the nucleus. The higher the energy, the different the wavelength in the photon test, the different colors you get. What happens here is when an electron falls to a lower energy level, a photon is emitted, and that is called emission. So what happens is when you excite the atom, that excitement, that energy, causes the electrons to move up in energy levels. And then they are constantly trying to get back to their normal energy level. As they fall back down to the lower energy level, they give off this photon. That is the emission, and that's how you get the different colors. Energy must be added to an atom in order to move an electron from a lower energy level to a higher energy level, and that taking on that energy by adding the energy is called absorption. So this shows here's absorption, here's energy being added, the electron absorbing it and moving up to a higher energy level. And then when emission is occurring, that electron is falling down back to its original energy level, which is a lower energy level, and in doing so, it emits the photon. And you can see mathematically, okay, how this works out as well in this diagram. All right, gentlemen, we are going to go ahead and move into section 2, which is going to specifically talk about the quantum model of the atom. And it's important to remember here that these theories of the atom are just building. It's one scientist building on the knowledge and work that was found by a previous scientist. So you're going to need to be able to discuss Louis de Broglie's role in the development of the quantum model of the atom, compare and contrast the Bohr model and the quantum model of the atom, explain how the Heisenberg uncertainty principle and the Schrödinger wave equation led to the idea of atomic orbitals, list the 4 quantum numbers and describe their significance, and relate the number of sublevels corresponding to each of an atom's main energy levels, the number of orbitals per sublevel, and the number of orbitals per main energy level. So to begin, we have all that conversation we had and discussion about light being particle-like and light being wave-like and the work of photons and cathodes and all that. Louis de Broglie comes along and he suggests that electrons can be considered waves, and in fact waves that are confined to space around an atomic nucleus. But if they can be considered waves, then that means there are certain wave properties that can be measured of these electrons and used to describe them. So he further postulates that if these electrons are waves, they can only exist at specific frequencies. Remember, frequency is specifically something that we measure in terms of waves, and it's a property of waves, okay? And he uses the relationship mathematically produced, what we talked about before, to show that frequencies are corresponded to specific energies, and those specific energies are the quantized energies of Bohr's orbits. Remember Bohr's experiment, he figured these quantums, and those are just measurements of energy, and what de Broglie says as well, if we can think of these electrons as waves, then those energies that we have must specifically discuss or speak to where those electrons can be. So, electrons, like light waves, can be bent or diffracted. This is another aspect. We know that waves can be bent, and diffraction is the term that we use to point to or refer to the bending of a wave as it passes by the edge of an object or through a small opening. Okay, this idea of diffraction, bending of light waves, this is like when you look down into a pond and you see a fish. The fish is not exactly where you see it, it's up above a little bit, because the light waves that are coming, bouncing off the fish and then bending through the water, give you an angle of refraction, which means the fish is not exactly where you see it. Also, if these electrons are functioning as waves, then it would follow that electron beams, like waves, can interfere with each other. If you have two waves coming from opposite directions or perpendicular to each other and these waves run into each other, it causes what we call interference. And interference basically occurs when waves overlap. This leads to what is known as the Heisenberg uncertainty principle, and this is where Werner Heisenberg comes in as a physicist, and he proposes that any attempt to locate a specific electron with a photon knocks the electron off its course. This makes sense if we go back to and think about what we've talked about in terms of understanding of particles and understanding of waves. The point is, if you use this experimental procedure to locate an electron, now you are not able to determine the position and velocity of an electron or any other particle because the photon is knocking it off its course to begin with. So these end up being uncertain probabilities and uncertain amounts, quantitative data, and it becomes known as the Heisenberg uncertainty principle. Schrödinger comes along in 1926. He's Austrian, and he says, well, if these electrons really are waves, and there's so many aspects of waves that are measurable, we should be able to come up with an equation that treats electrons as waves. And he does that, okay? And basically when we take Heisenberg's uncertainty principle and Schrödinger's wave equation, this ends up being the founding of what is and exists today as the modern quantum theory of the atom, okay? We moved from Bohr's orbital model to the quantum model based on the work of these guys, which looks at the electrons and treats the electrons as waves. So quantum theory describes mathematically the wave properties of electrons and other small particles. We tend to focus on using quantum theory specifically to discuss these wave properties of electrons. So the first thing, if you're going to look at Bohr's model was also known as the orbital model, and what Bohr said was electrons followed these these very clean paths or orbits around the nucleus. If you looked at a model of an atom, it looked like a model of the universe. You would have the sun or the nucleus at the center, and you would have these very distinct orbits that went around the sun. The quantum model says that the electrons do not travel around the nucleus in neat orbits. So there's a difference there between the quantum model and Bohr's model. Instead, the electrons exist in a region, okay, not a neat path or orbit, but a region, and we call those region orbitals. We're still holding on to some of the characteristics of Bohr's model, but we're understanding it at a deeper level. What an orbital is not this neat one-dimensional path, okay, in space, but an orbital is a three-dimensional region that exists around the nucleus that indicates the probable location of an electron. So these are based on math. These are based on mathematical calculations. And what we've done is we've been able to come up with, quantify this information. We have these quantum numbers that specify properties of atomic orbitals and the properties of electrons in the orbitals. And there's 4 numbers, okay, that we specifically use. And you're going to need to learn this stuff, guys. You need to take the time to go and read the chapters carefully and fill in a lot of what you get in the lecture. The principal quantum number is symbolized by lowercase n, and that indicates the main energy level occupied by an electron. So N1 is energy level 1, N2 is energy level 2, N3 is energy level 3. Okay, and when you draw these in kind of one-dimensional space on your paper or on a board, you can draw them, and they look like, really, orbits going out in concentric circles from the nucleus of the atom. The next thing we talk about is the angular momentum quantum number. That's symbolized by L, and that indicates the shape of the orbital. So we can have the main energy level, 1. We can describe the shape of the orbital, 2. We can look at the magnetic quantum number, lowercase m, which is describing the orientation of the orbital, so that's 3. And then the spin quantum number, which only has 2 possible values, positive 1/2 or negative 1/2, which basically indicates that the electron is either spinning in one direction or spinning in the other direction. This diagram shows you the different orbitals, okay? The orbitals, we specifically talk about S, P, and D. There's also F. S is the round orbital. There's only one S orbital for each energy level. So energy level 1 has one S orbital. Energy level 2 has one S orbital. Okay, energy level 3 has one S orbital. Then we go to the P orbitals. Notice the P orbitals are dumbbell shaped, and there are 3 P orbitals for each energy level. So energy level 2 has one S orbital and 3 P orbitals. And you can see the P orbitals are dumbbell shaped, oriented on the z-axis, the y-axis, and the x-axis. Then we get to D. And with the D orbitals, there are 5. They start with energy level 3. So what this means is energy level 3 has one S orbital. It has 3 P orbitals, and it has 5 D orbitals. And you can see those 5 different shapes and orientations right there. So again, you really need to make sure you work through understanding this concept. This chart shows us each energy level, the sublevels available, or the orbital sublevels. Okay, we go S, P, D, F through 4. It shows us the number of orbitals in each sublevel. S has 1, P has 3, D has 5, F has 7. It shows us the number of electrons possible in each sublevel. So the S orbital sublevel holds 2 electrons. And the first energy level only has an S orbital sublevel, and therefore only holds a total of 2 electrons. Well, if you get up to the 4th energy level, that has an S, P, D, and F sublevel. Therefore, 1 orbital in S, 3 in P, 5 in D, 7 in F. Each one of those 2 electrons per orbital, so 2 for S, 6 for P, 10 for D, 14 for F, and therefore the fourth energy level can hold a total of 32 electrons. This can go on up through 6. Notice the asterisks. In most cases, we get beyond F, and they're not really needed in the ground state. And then finally, we have this chart, which will describe in a different way the orbital name, the N, the L, and the M numbers, and the number of orbitals in each one. Now we're going to take all of this, guys, and put it together in the last section. We'll see how this plays out in describing these atoms and their electrons. All right, gentlemen, this is going now take us into section 3, which is going to begin to lay out, based on the information that we just discussed, lay out for us the electron configurations in atoms and actually doing that work. So, things that you're going to need to be able to do after going through this chapter: list the total number of electrons needed to fully occupy each main energy level. That means you're going to need to know the number of orbitals, sublevels, and orbitals in those energy levels. State the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Describe the electron configuration for atoms of any element using orbital notation, electron configuration notation, and, when appropriate, noble gas notation. So electron configurations. What this is now got us to, everything we've already talked about, is that we can describe the configuration of electrons in any atom. And the arrangement of electrons in an atom is known as the atom's electron configuration. The lowest energy arrangement of the electrons for each element is called the element's ground state electron configuration. So where we are arranging, or we are looking at the arrangement of atoms in the lowest energy state, that is the ground state electron configuration. This shows how energy increases. So for example, you have 1s. 1s would be the first energy level and your s orbital. 2s, of course, would be the second level, but the s orbital. 2p is just a little bit higher in energy, where you're still in the second energy level, but you are now in the p orbitals. 3s would be the third energy level, okay, but the s orbital. 3p is the third energy level, but the p orbitals. Notice, though, that in this case, now at this point, 4s comes before 3d. What that means is 3d actually has more energy. That is the third energy level, the d sublevel, the d orbitals. 3d has more energy than 4s. So notice that slip there. After 3d comes 4p. But next would be 5s. We list these based on their energy. So 5s is going to have a little bit less energy than 4d. And then 5p is going to have more energy than 4d, but less energy than 6s, I'm sorry. Now, this line over here on the left, 1s, 2s, 2p, 3s, 3p, 4s, 3d, that's important because in order to fill electrons into their appropriate places, it has to happen in that order. So it's not as easy as 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. It doesn't work like that. And you should memorize this order. There's also other tools and tricks that you can use. So there are some rules that we follow when we're talking about electron configurations. The first is the Aufbau principle. which basically states that an electron occupies the lowest energy orbital that can receive it. When you are working through these problems and putting electrons in their orbitals, you always put electrons in the lowest energy orbital that can receive it first. And we also follow the Pauli exclusion principle. The Pauli exclusion principle basically states no two electrons in the same atom can have the same set of 4 quantum numbers. So why is this an exclusion principle? What that basically states, guys, is once an electron is in a spot, no other electron can be in that spot. We also talk about Hund's rule, which basically states orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second electron. And all electrons in singly occupied orbitals must have the same spin state. And I think these things will make sense as we start to look at some of the practice problems and work through them. Now, how do we do this? How do we represent electron configurations? The question really is, how do you on paper show where these electrons are? The first is orbital notation. An unoccupied orbital is represented by a line with the orbital's name written underneath the line. And so an orbital containing one electron is represented this way. So there's the line, and there's the up arrow. The up arrow you're going to see represents the spin of the electron. Remember, every orbital can only hold a particular number of electrons, 2 electrons per orbital. The more orbitals you have in an energy level, the more electrons that energy level can hold. But we're really talking about 2 electrons per orbital. So we said that the first energy level has 1 orbital. That's the s orbital. That's the spherical one. That one s orbital can hold up to 2 electrons, no more than 2. So the first energy level will only ever have up to 2 electrons in it. No more than 2. Now, what this means conceptually, guys, is that an atom that has lots of electrons is going to have lots of energy levels and lots of orbitals, because the electrons are going to fill from the lowest energy level to the highest energy level. They're going to fill the orbitals in order. But hydrogen, for example, that has an atomic number of 1 and therefore 1 proton, is going to have 1 electron. That electron is going to go into the 1s orbital, the first energy level in the s orbital. Now that orbital can hold up to 2. So when you get to helium and you've got 2, there's going to be 2 in that s orbital. But when you get to 3, 1s is done. Because there's only the s orbital in the first energy level, you've got to move up to the second energy level and start with s again. Now, if the orbital contains 2 electrons, remember, every orbital is going to be represented by a line. If it contains 2 electrons, you're going to represent the second electron with an arrow, but it's going to be an arrow facing in the opposite direction to show that one electron has a spin orientation in one direction and that the other electron has a spin orientation in the opposite direction. And the lines are labeled with the principal quantum number and sub-level letter. For example, the orbital notation for helium is written as follows. Helium, 1 line, and what energy level is that? It is the first energy level. And what orbital is that? It is the s orbital. And how many electrons is there? 2. 1 arrow facing up, 1 arrow facing down. And that's it for helium, because there's only 2 electrons in helium. We can also do electron configuration notation. So this is a little different. Electron configuration notation eliminates the lines and arrows of the orbital notation. And what we have instead is the number of electrons in a sublevel is shown by adding a superscript to the sublevel designation. So it looks something like this. The helium configuration is represented by 1 S2. So it would be helium. The number 1 represents the energy level. It's the first. The S represents the orbital. The first energy level only has the s orbital. The superscript 2 represents the number of electrons in that s orbital, which is 2. As it says here, the superscript indicates that there are 2 electrons in helium's 1s orbital. So what does this look like in terms of doing a sample problem? The electron configuration of boron is 1s2, 2s2, 2p1. How many electrons are present in an atom of boron? What is the atomic number for boron? Write the orbital notation for boron. So first thing I want you to note, guys, what's interesting, out of that simple notation that's given, there's several different pieces of information that you can infer from that. So first, number of electrons in a boron atom is equal to the sum of the superscripts in its electron configuration notation. So 2 plus 2 plus 1 equals 5. So there's 5 electrons. Those superscripts will all, in electron configuration, those superscripts will always be equal to the number of atoms. The number of protons equals the number of electrons, or I'm sorry, those superscripts will always be equal to the number of electrons. The number of protons equals the number of electrons in a neutral atom. So we know that boron has 5 protons and thus has an atomic number of 5. To write the orbital notation, first draw the lines representing the orbitals. Right? You have 1s, you have 2s. You know that there is a p orbital. And p has 3 suborbitals. So you would have 3 lines under the 2p orbital, or under the 2p energy level. And all you got to do now is fill in the electrons appropriately for each one of those sublevel orbitals. You add the arrows to do that. First 2 electrons occupy the first energy level and fill the 1s orbital. So 1 up arrow, 1 down arrow. The next 3 electrons occupy the 2 second energy level. 2 of those occupy the lowest energy level, which is 2s, so you always fill. And the third occupies a higher energy level, p. So it looks like that. And notice you have 5 up and down arrows for your 5 electrons. Now we'll move to elements of the second period. In first period elements, hydrogen and helium, electrons occupy the orbital of the first main energy level. According to the Aufbau principle, after the 1s orbital is filled, the next electron occupies the s sublevel in the second main energy level. We already saw that. You're going to go up by energies, but this is where it gets confusing, and you're really going to have to puzzle through some of these to get it figured out. The highest occupied energy level is the electron-containing main energy level with the highest principal quantum number. So now we have inner shell electrons, are electrons that are not in the highest occupied energy level. The way you can think about this orbitally is that the highest occupied energy level is going to be, if you were to draw these as orbits, okay? If you were to draw these as orbits, the orbit farthest from the nucleus would be the highest occupied energy level. Inner shell electrons would be electrons that are not in that highest occupied energy level, or that orbit farthest out. Okay, they would be the electrons that fall somewhere between the nucleus and that farthest shell, or that farthest orbit out. So how do we write electron configurations? First thing we have to do is figure out the number of electrons. Then we have to figure out the order of filling orbitals. And as I said before, it goes by energy. It does not go just in order. It doesn't go 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. And you see where you have that pyramid or that triangle? This is an easy way. Again, what I have always told my chemistry students, if you want to do these correctly, you need to memorize this triangle. So you write down this triangle 1s. You write down 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then you start the next row up 2p, but 2p goes above the 2s, and you go across 3p, 4p, and then d goes above the 3s, 3d, and then 4, okay? Now follow the arrows. See that arrow, squiggly arrow? You start with 1s, you fill 1s first. Then you go from 1s to 2s. You go from 2s to 2p. You go from 2p to 3s. 3s to 3p. But now, instead of going from 3p to 3d, you go from 3p to 4s. 4s comes before, and after 4s, you go all the way up to 3d. And then 3d to 4p to 5s. Okay, so that is the order of filling orbitals, meaning you put the electrons in that order. Notice on the bottom here, everything else is still written in what you would think of as the logical order. 1s, 2s, your 3 orbitals in 2p, 3s, 3 orbitals in 3p, 5 orbitals in 3d, then 4s. But you're going to fill the electrons in according to the order in that triangle. After the outer octet is filled in neon, the next electron enters the s sublevel in the third energy level. And that takes us to noble gas notation. Okay, here we're looking at the group 18 elements. These are the noble gases: helium, neon, argon, krypton, xenon, and radon. These are called the noble gases. And a noble gas configuration refers to an outer main energy level occupied in most cases by 8 electrons. The reason why, guys, these are called noble gases, they're also known as inert gases, is because their outer level is filled with 8. Okay, that's the octet rule. They're filled with 8. Okay, that's what a stable atom wants. It wants 8 in its outer shell, okay, so to speak. And because these noble gases have 8, they're not very reactive. They don't react with things because they're completely stable because they have 8 electrons in that last energy level, or that main energy level. Okay, so this shows each one of those, and it shows how each one is filled. Move on to the fourth period, filling the 4s orbital, the empty orbital of lowest energy. With the 4s sublevel filled, 4p and 3d sublevels are the next available vacant orbitals. Again, notice the order, you're filling them by energy. The 3d sublevel is lower in energy than the 4p, therefore the 5 3d orbitals are next to be filled. This is just going by period. Now we're going down through the periodic table for argon and potassium. Fifth period. In the 18 elements of the fifth period, sublevels fill in a similar manner as in the fourth. Successive electrons are added first to the 5s, then to the 4d, and finally to the 5p. So let's take a look at a sample problem and see how this plays out. Right, both the complete electron configuration notation and the noble gas notation for iron. So how many electron-containing orbitals are in an atom of iron? How many of these orbitals are completely filled? How many unpaired electrons are there in an atom of iron? And which sublevel are the unpaired electrons located in? When we do this and we do it properly, we can figure all that information out. Alright, so the complete electron configuration notation of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. And it's Noble gas notation is 3d6 4s2. Note, it's wherever the last 8 electrons are is what you use to show the noble gas notation. It has 15 orbitals that contain electrons. S, S, and then P, right? But how many orbitals are in P? That's 3. So I've got 1, 2, 3, 4, 5. S would be 6. P is 3 again. So that's 9. D is 5. So that's 14. S would be 1 again. So that's 15. Remember, S always has 1 orbital. P always has 3 orbitals. D always has 5 orbitals. They consist of 1 1s orbital, 1 2s orbital, 3 2p orbitals, 1 3s orbital, 3 3p orbitals, 5 3d orbitals, and 1 4s orbital. 11 of the orbitals are filled, and there are 4 unpaired electrons. How do we know that? Well, again, we're looking and seeing where the electrons are in the 3D sublevel, right? Because you could have up to 10 electrons. In the 3D sublevel, there would be 5 orbitals, 2 electrons for each orbital. Okay, but you're going to fill not just in straight order, but you fill according to that triangle. And whatever's left gets put back over here in 3D. The notation 3d6 would look like this. 3D, there's your lines. You would put 1 arrow, then on the next line an 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 arrow. You never put 2, 2, 2. You always fill 1, 1, 1, and then you go back and put your second one in on each one. Write both the complete electron configuration notation and the noble gas notation for a rubidium atom. Identify the elements in the second, third, and fourth periods that have the same number of highest energy level electrons. So we go and we find the number of electrons, we write it out, making sure that we fill the sublevels appropriately. Your noble gas configuration, this time you have that. It has 1 electron in its highest energy level, the 5th. The elements with the same outermost configuration are in the second period lithium, third period sodium, fourth period potassium.